So my name is Hunter Hamby. I'm doing a presentation over a closed form electrical energy approximation for an n-particle ring. Big scary title, I know. So what exactly are we doing? So we're considering two charge configurations. The first charge configuration is a ring with charged particles evenly spaced around it. So you have a charge, and then the second charge, and then the third charge, and they're all the same distance away from their partner. And then the next configuration, we do that with n-1 charged particles, except the one we took out, we've now put in the center. So now we're looking at how much energy it takes to make this. Okay, so there's a well-known formula for charged particles on a ring. It's got some constants in it, it's got a sum, scary math stuff. But anyway, this tells us how we need to calculate the energy of this configuration. So we need to add up all the distances from the charges and multiply it by some numbers, and we get our answer. So we go through, we do some fancy math stuff. We find out that our formula is a sum over cosecants times some numbers for the first configuration, and then for the second configuration, it's a sum over cosecants times some numbers plus another term. Doesn't really matter, but that's what we find out. So the problem is that we wanted to close this sum, meaning if you give us an n, we put it in a little formula and it spits out the energy. Problem is this sum can't be closed, so we're going to have to approximate it. With some more fancy footwork, we approximate it. We use some analysis techniques and calculus, and it's got a whole bunch of natural logs and cotangents and cosecants, so I won't scare you with it here, but just know that it exists. It's scary, but it does work. So how good is it? Well, while we can't close the sum ourselves, analytically, we can put it in a computer, and computers are real good at adding, so they add it all up, and it finds us the exact answer. And then to find out how good it is, we subtract off what we got from the right answer and find the percent error. So how good was it? For the first configuration, the max percent error we had was 3.5%, meaning we're only about 3.5% off, which in science we want a 95% interval, so that's pretty good. The second configuration, we had a 2.5% error at max, which still is even better, so that's good. But the more important news is that it seems that the error goes to 0 as the number of particles increases, which is what we expect. So it's following trends we like. That's good. So what does all this mean? Well, even though there's a bunch of scary math going on, physically what we're modeling is, energy configurations. Nature likes low energy. Nature likes to not use a lot of energy. It likes to stay away from each other, it likes to chill out, do its own thing. So physically what we can model is if we put charges on a ring, how should they look in the lab? Or if we have some kind of shape and we put charges on it, where will those charges situate themselves so the lowest energy is found? So what we found was that in the first configuration, it is less energetic until you use 12 charges. And in the second configuration at 12 charges, that becomes less energetic. So if we're in the lab and we're putting charges on a ring, as soon as we put 12 on there, one should come off and sit itself in the middle because nature likes low energy. So that's interesting. So mathematically, what did we learn? Well, mathematically, this tells us about the growth rate of the functions modeling these physical things. So the growth rate for the first function is faster because it overtakes the second function at some point, which will help us deduce some ideas about the sum, how we can close it, what it looks like at large numbers, all these things. So why did we do all this? Largely right now the problem is a novelty. It's kind of a fun little textbook problem, but there are some applications, like I said, mathematically. It gives us some insight into the growth of the functions so we can, model how they look and see if we can close that sum. And physically, like I said, it talks about energy configurations, which is always good in physics because nature likes low energy. and we want to study nature.